This tutorial will illustrate several ways in which composite columns may be defined for use in ETABS. There are two primary types of composite columns in ETABS, those in which a steel section is filled with concrete, and those in which a steel section is embedded or encased in concrete. There are also two different ways to create these sections, using either these parametrically defined section types under the steel composite heading, or using the section designer utility located under the special heading. We will create the same filled tube section using both methods to compare the two techniques. We start by clicking the Filled Box Tube Section button. We will name the section Composite Column 1. Note that the material for the steel is A992. Materials are important to determine the correct equivalent properties. Verify that the section shape is set to filled tube and enter a total depth and width of 24 inches and a flange and web thickness of 1 inch. We will use no corner radius to make our verification calculations simpler. Verify that the fill is 4,000 psi concrete. And with the section defined, we can review the calculated section properties. The properties shown have been calculated for an equivalent section using a steel base material. We can easily change to a base material of concrete, and the properties are recalculated. We will take a look at these values later after using the section designer. Next, we will define the same exact composite column using the section designer. We will name our second section Composite Column 2. And we'll leave the base material as 4,000 psi concrete, although it can be any of the other defined materials. The base material is the material that will be used to report the equivalent properties. Under Design Type, we will select the Composite Column option and then click the Section Designer button to start the Section Designer utility. Once again, we will create a steel tube filled with concrete. We start by drawing the steel section. We locate it with a single click. A right click on the shape displays the object data form where we can set the properties. Make sure that the material for the tube is set to A992. This matches the previously defined section, and verify that the height and width are 24 inches and that the thicknesses are 1 inch. Again, no corner radius will be used. Click OK to close the form. Now we will add the concrete fill by drawing a concrete shape. We will center the concrete rectangle at the same location as our tube. If we go to the Edit menu, check Section for Overlaps command, the message indicates that the concrete shape added extends past the steel tube, so we will need to revise the concrete shape. A right click on the concrete shape displays the object data form where we confirm that the material is 4,000 psi concrete as desired. However, the size of the concrete is too large. It should be the size of the tube less the thickness of the tube walls, or 22 inches square. Checking again for overlaps, shows that the concrete is now contained completely within the steel tube as desired. Our Section Designer composite column is now complete, so we can review the section properties. Remember that these properties are in terms of the base material, concrete. If we bring back results from our first composite column that was generated parametrically by the program, we see that the area and moment of inertias are identical. There are slight differences in the shear areas due to the fact that the Section Designer uses a more sophisticated analytical technique rather than published formulas. Since the two program approaches match, let's do a hand calculation to verify the results. We will check the axial area. The modulus of elasticity for our concrete is 3,604,996, and for the steel it is 29 million. We want to come up with the equivalent area using concrete. So the area will be the ratio of the two moduli times the area of steel plus the area of concrete, which gives us 1,224.08. The number matches and thus confirms the program output. Now that we have shown how to define a composite column, we will use a composite column in a building model. Here we have created a simple 6-story building using composite column 1. We can see the column shape in the plan view. And a right click on a column in the 3D view shows that the assigned section is composite column 1 and that the design procedure has automatically been set by the program to perform composite design. The analysis has already been run, so we may proceed on to the design. Going to the composite column design, we will first review the design preferences. Now, we are ready to start design of the columns. Once design is complete, we can right-click on the composite column to display the design results. Note how small the demand-capacity ratios are due to the large capacity of the composite column. Clicking on the summary displays the detailed design calculation report. This concludes this tutorial on creating composite columns in ETABS.